Hey, welcome back. Thermite here. This is part 2 of our tank tutorial. We'll be converting our electric tank to a big dirty diesel engine. If you watched the previous tutorial, you'll remember how we were able to make an easily controllable tank prototype with electric motors driving it. Well, it's demolition time. Let's get rid of these electric motors and our electric drive microcontroller. We'll delete these pipes as well since we'll have to route the power from a different location. We're also going to raise the front drive sprocket to make it look the part. Let's get some pipes going back to behind the seat, since that's where we'll put the engine. We'll also raise the rear wheels to give it that nice trapezoidal shape. Now, let's grab a crankshaft for our engine. We'll use the 3x3 modular engine for this tutorial. There. Let's grab some cylinders. 2 cylinders will be more than enough power for this little thing. When placing cylinders as shown, they share all fluids such as air, fuel, exhaust, and coolant. Now we'll slap a belt drive on the front of it, so we can put some starters and alternators. We'll put a 3x3 clutch on next. It's very important that you use all the same sized engine parts. Use 3x3 parts for 3x3 engines, and 1x1 for 1x1 engines and so on. Now some starters, and then a couple alternators. Now we'll place a constant number set at 1 to keep the alternators making power. And while we're here, we'll replace this huge battery with a small one. We only need enough electricity to start our diesel. We'll add a gearbox next to get more RPS out of our engine. I'll just put it at a 9:5 ratio for now. We can adjust it later if we need more RPS or more torque. Then we'll tee out our drive shaft to go to each set of tracks. Now let's start adding our manifolds to the engine. We'll start with our air manifold. Remember, all fluids will be shared between these cylinders since they're in line with each other. Next we'll add our exhaust. Then our coolant. And finally, our fuel. Let's go ahead and place a fuel tank and route our fuel line. Now that that's done, let's route our coolant and figure out where to put our radiator. I'm thinking I'll put it underneath the engine. Nice. We have fuel and cooling done so far. Now let's add an air filter. Boink. Now an exhaust port. Boosh. Now we're going to venture into the microcontroller editor to make a simple engine controller for our diesel. This controller will be able to control the engine's RPS, starter, and air and fuel manifolds. We'll need a 3x2 microcontroller with 6 nodes. We'll start by making the ignition node. This will take a toggle input like a key and turn the engine on. Next we'll make a node for RPS. This will be important for limiting how much our engine revs. Now we'll make a node for air and a node for fuel. These will be calculated within the microcontroller. The next node we'll make is the starter node. We don't want our starters wasting power if the engine is already running, so we'll have this node with some logic to tell the starters when to engage. Lastly, we'll make the throttle node. This is how we'll control our engine. Now let's get to the logic. First we'll organize our nodes, then we'll get started with controlling our throttle. Alright, we'll grab a 3-input function block to begin with. This will be how we convert the -1 to 1 numbers that the throttle gives to the RPS that we want the engine to run at. We'll grab a property number so that we can configure some numbers later if we want. One is for our maximum RPS, and the other is for our idle RPS. For now, we'll put 15 RPS in as our max. This is higher than I normally put myself, but it makes it a little easier if you haven't messed around much with gearboxes. For our idle RPS, we'll put 3.5. Diesel engines in Stormworks stall at less than 2 RPS, so a little buffer from that can be nice. We'll hook up these to the function block, and we'll clamp our throttle between our idle and max RPS properties, and also times the throttle by our max RPS. Next, we'll add a PID controller. This is what will control our RPS based on our throttle input. The PID controller measures the error between the process variable and the set point. The set point being where you want your value to go, and the process variable being where it currently is. So, we'll connect the function block to the set point node and our RPS node to the process variable node. Then we'll put 0.3 for the proportional gain value in the PID controller. Next, we'll clamp the output from the PID between 0 and 1. By the way, make sure you connect the activate PID node to the ignition node, or else it will not work. Now we'll grab a single input function block. We'll connect the air node straight from the clamp, but we'll take the output from the clamp through the having function and hook it up to the fuel node. Okay, that's the throttle taken care of. Now we'll move on to the starter. If we just hooked it directly to the ignition, it would constantly engage the starter, and you would be annoyed to death by the sound, and your battery would also die a somewhat related death. So, instead of that, we'll use a less than logic gate and hook up input A to our RPS. Next, we'll use a constant number block to hook up to input B of the less than. We'll set the constant number to 2.25. Remember, the engine stalls at less than 2, and a little buffer is good. We have an AND gate right after the less than gate. Wheel that up to input A, and the ignition will connect to input B, so that if the RPS is less than 2.25 and the ignition is on, then the starter will engage. Only if both conditions are met will the starter engage. Alright, let's double check that I did it right. Okay, looks good. So there's our diesel engine microcontroller. If you have questions about this microcontroller, don't hesitate to reach out. Let's save it and stick it on our build. Now let's connect the logic. We'll need to place a key down so we can connect our ignition node to it. Now that that's taken care of, let's wire up some electricity. Alright, let's test out our new engine controller complete with RPS control and auto starter. Oh yeah, I forgot. That dial is for speed. Let's put another for RPS so we can visualize what the engine is doing. So, our engine idles nicely and revs up to our max RPS. For now it only revs when we press W. We'll need to make another microcontroller to adapt this to work for a tank. You might wonder why we didn't make it for a tank. I did this because this engine controller can be used for any naturally aspirated modular engine. A lot of plug-and-play capability with microcontrollers is very useful and time-saving for me personally, even if I have to make an extra microcontroller for specific use cases once in a while. Anyway, let's make an adapter to rev the throttle when any direction is pressed on the seat. This can be a very small 1 by 2 microcontroller. We'll add a couple nodes, one a composite input to take the seat composite node, and the other a number output to send the throttle to our engine microcontroller. Let's figure out some logic. We'll need to read the composite node and separate it into channel 1, and channel 2 for A and D, and W and S, respectively. You may think that all you need to do is add the two channels together, but since both axes go to -1, this doesn't meet our needs. Instead, we need a logic gate called ABS, which returns the absolute value of a number. This simply means that any number that was negative becomes positive. And just like that, our microcontroller for adapting our throttle to work for a tank is complete. We'll place it down and hook it up. Don't forget your composite node. We'll save it and spawn it in to check if the throttle adapter works as intended. W S A D. It all works perfectly. Now we're going to work out the clutches. We're going to use 1x1 modular engine clutches on either end of a 1x1 crankshaft. We'll use 2 of these clutches on each side. We'll place down a gearbox for reverse by 1 set of clutches. The reason for using the modular clutches instead of the standard 2x1 clutches is because power is not delivered until over 0.3 for the standard clutches, but is almost immediate for the modular clutches. This simplifies the clutch microcontroller slightly. Make sure to hook up the 3x3 modular clutch to a constant number 1. That's the component side of things done. Now back to the microcontroller editor. We'll make it a 2x3 microcontroller with 5 nodes. 1 composite node for the seat and 4 number outputs for the 4 clutches. Let's name the microcontroller and save it. Now the logic. As always, separate out the nodes and organize them. Let's take our composite readers and read channels 1 and 2. Note channel 2 is on top. We'll need 2 single input function blocks. We'll enter -x into both of them and hook them into their corresponding readers. Next, we'll take 4 add blocks and place them just before the clutch output nodes. Now we connect the logic like so. Now we have a lovely little spider web of confusion. I have no idea what I'm doing. I'm sure it'll turn out fine. Slap this right here, connect it up, and see what in the world I've created. Man, this AI voice sounds so confident about this. Obligatory reminder about composite nodes. Cool, now let's test it. Huh, awkward. Well, back to the drawing board. Note to self, things don't work if you don't hook them up. Well, let's see if my marvelous engineering skills triumph this time. Yowza, we fast. Still can't turn though. Hey, guess what? If you don't have a reverse gear, you can't go in reverse. Groundbreaking, I know. Sigh, I'll get the hang of this game in a few more thousand hours. Hey, looky there. It's almost like you need to configure things correctly for them to work. That neutral steering looks really good. It's a little bit short on top speed, but we only went with a 9:5 ratio on the gearbox. Let's go crank that up to a 3:1 ratio. Now, let's see if our top speed increases. It looks like we're topping out at around 36 meters per second, which is approximately faster than your average nuclear manhole cover. In other words, 80 miles per hour. And there you have it, folks, the Stormworks tank tutorial part 2. I hope you were able to follow this train wreck from beginning to end. Hopefully it was useful in some way to you. I know this is not a completely realistic way to make a tank, but it was by far the smoothest system for it that I've made. Live long, and may the force be ever in your favor.